In this tutorial, I'm going to cover MetroCluster, which is NetApp's solution for redundancy for your storage system across two different buildings within the same geographical region. Before I get into the details of MetroCluster though, it's going to make it easier to understand this if we have a quick review of plain high availability first. So looking at the diagram here, I've got my standard high availability pair, controller 1 and controller 2. In NetApp ONTAP, our disks are always owned by one and only one controller. Our disks are grouped into our aggregates, and you see in the diagram here that aggregate 1 is owned by controller 1 and aggregate 2 is owned by controller 2. High availability gives us redundancy for our controllers. So if controller 1 fails, then controller 2, its high availability partner, is going to detect that. It can either detect it over the high availability connection, or it can also detect it using the service processors with hardware assisted failover. When controller 2 detects that controller 1 has failed, it will take temporary ownership of its disks. So as you see here, controller 2 is now owning aggregate 1 and aggregate 2, and our clients are still able to reach all of their data. So high availability helps when we have a controller failure, but what if the whole building goes down? So in the example now, I've got controller 1 and its disk shelves are in one building, controller 2 and its disk shelves are in a different building. And this time it's not just the controller that fails, we lose the whole building. So I have a power outage, for example, there. So I've lost my controller and I've lost my disk shelves as well. Now controller 2 will still detect that over the high availability connection because it's not going to still be receiving keep alives. But the problem is that it can't take control of the aggregate 1 because the disk shelves are gone. Aggregate 1 isn't there anymore, it's failed. So high availability, it gives us redundancy for our controllers, but it doesn't give us redundancy in case we lose the entire building. And that's where MetroCluster comes in. So MetroCluster gives us redundancy in case of a building failure by combining high availability and sync mirror. Sync mirror is used to mirror the aggregates to a disk shelf in each building. So high availability gives us the redundancy for our controllers. Sync mirror gives us redundancy for our disk shelves. So by combining the two, we get redundancy for the entire building. We can selectively choose which aggregates to mirror if we want. We could either mirror all of them, or we can cut down on disk hardware costs by only mirroring our mission critical aggregates. So let's take a look at how MetroCluster is going to work. You can see here I've got my two controllers again, controller 1 in one building, controller 2 in another building. Controller 1's got its disk shelves and controller 2 has got its disk shelves. But what we do now is aggregate 1 is still owned by controller 1, but I have it sync mirrored across the two buildings. So Plex 0 is in one building, Plex 1 is in the other building. And I do that for aggregate 2 as well. If building 1 fails, I lose the controller and I lose the disk shelves. But because aggregate 1 and aggregate 2 are still available, both of them in the other building, my clients don't lose access to any of their data. For the switchover to the second building, that can either be done manually or we can use automatic switchover. I'll go into more detail on that later in this lesson. Sync mirror, and therefore MetroCluster, uses synchronous replication. Data is written to both buildings before the acknowledgement is sent back to the client. Because it's synchronous replication, MetroCluster has a recovery point objective of 0. No data is lost in the case of an outage. There's been a few different implementations of MetroCluster in clustered data ONTAP. It first became available in ONTAP version 8.3.0. That's actually the version that 7 mode was discontinued in. MetroCluster had been available in 7 mode for quite a while, and really it was pretty much the last major feature to be ported over to cluster data ONTAP. So once MetroCluster was available in version 8.3.0, because it was really the last major feature to get moved over, that's why 7 mode was discontinued at that point. In ONTAP 8.3.0, MetroCluster supports a 4-node setup only. This configuration is also available in later versions of ONTAP as well. With the 4-node MetroCluster setup, both sites host an independent 2-node cluster. With MetroCluster, it's always 2 sites. We can't have like 3 or 4 sites. It's always going to be 2. The 2 nodes in each site are an HA pair for each other. Sync mirror mirrors the aggregates across both sites. Okay, so not across both nodes in the same site, across both sites. It's an active-active configuration. Each site serves read data to local clients from the local plex. If a single controller fails, the main controller in the same site will take over its aggregates, just like in standard high availability. If both controllers in a site go down, meaning the entire site is down, you can fail over to the other site. And the sites can be up to 200 kilometers apart. We have a controller to shelf distance problem because SAS is used for the controller to disk shelf connections, and SAS only supports short cable lengths. So how can we cable controllers to a disk shelf in another building? Well, what does support long length cables is fiber channel. So a pair of fiber channel switches will be installed in both sites. But now we have the next problem where the current models of disk shelves have SAS, not fiber channel ports. So if we're using these long distance fiber channel cables to go from the controller to the shelves in the other site, how are we going to actually get the cable into the disk shelf? And that's where the ATO fiber bridge comes in. It's a fiber channel to SAS gateway. So we have a fiber channel port in there and a SAS port, and it can convert between the two. The controller connects to the fiber bridge with fiber channel cables via the fiber channel switches. And the fiber bridge connects to the disk shelves with SAS cables. This will look really clear when you see it in the diagram coming up in a minute. In fact, let's look at it right now. Let's look at the MetroCluster cabling for fabric attached MetroCluster. Fabric attached MetroCluster means we're using fiber channel switches. In the example here for our 4-node MetroCluster, we've got our HA pair in site 1. So that's site 1 controller 1 and site 1 controller 2. We also have our HA pair in building 2. That's site 2 controller 1 and site 2 controller 2. The next thing we're going to look at is our disk shelves. So over in building 1, we have aggregate 1 plex, which is owned by site 1 controller 1. And we have the sync mirror other plex for that, aggregate 1 plex 1 in the other site, again, which is owned by site 1 controller 1. We're also going to have a second aggregate, aggregate 2 plex 0, which is owned by controller 2 in site 1. And we have the plex 1 from sync mirror over in site 2 for that aggregate. Then we have a third aggregate, aggregate 3 plex 0, which is in site 2, which is owned by site 2 controller 1. And we have plex 1 for that, which is in site 1. Again, both plexes are owned by site 2 controller 1. And finally, we have aggregate 4, which is owned by site 2 controller 2. Plex 0 is in building 2, and plex 1 is in building 1. Now, in the example here, I've used 4 aggregates, and I've got a single stack of disk shelves in both sites. That's just to make the diagram really clear and easy to understand though. You can have as many aggregates as you want, and you can have multiple stacks in your different sites if you want to as well. Okay, next thing to look at is the 8 fiber bridges, and we're going to cable these up to our disk shelves. So in site 1, fiber bridge 1 gets connected to the top shelf in the stack. We then daisy chain the shelves going down from there, and then fiber bridge 2 is connected to the bottom shelf in the stack. So I do that in site 1, and I do a matching configuration in site 2 as well. The next thing that we need is our fiber channel switches. These are going to either come from Cisco or from Brocade. Fiber channel switch 2 gets connected to fiber bridge 2, and fiber channel switch 1 gets connected to fiber bridge 1. These are fiber channel cables. The cables you saw earlier going from the fiber bridge to the disk shelf are SAS cables. So I've got my fiber channel switches in site 1, and I'm going to have a similar setup in site 2 as well. Next thing to do is to cable my controllers to my fiber channel switches with fiber channel cables. So site 1 controller 1 gets connected to the first fiber channel switch, and it also gets connected to the second fiber channel switch. And I do the same for site 1 controller 2, it also gets connected to both switches. Now in the diagram here, I just showed one connection there to make it tidier in the diagram. There's actually 2 connections from each node to each switch. These are your node initiator connections, which give the controllers connectivity over fiber channel to the disk shelves in both sites. So those are my connections in site 1. I'll do similar connections also in site 2. So that gives my controllers connections to the disk shelves in the same site, but they need to have connections to the disk shelves in both sites because we're using sync mirror to write to both locations. So I connect my fiber channel switches together as well. Fiber channel switch 1 in both sites gets connected to each other, and I also connect fiber channel switch 2 in both sites to each other as well. Again, I've just shown one connection there, but you can have actually up to 4 connections between each pair of switches bundled into a port channel. And if you have a look at the diagram, you'll see there's no single points of failure. I've got 2 controllers in each site, which are configured as an HA pair for each other. I've got 2 fiber channel switches in each site, 2 fiber bridges in both sites, and my aggregates are sync mirrored across both sites as well. We're not quite done with the cabling yet though. The cabling in the previous diagram showed the node initiator connections from the controllers to the disk shelves in both sites for reads and for writing to disk during consistency points. Writes still work in the same way as usual though, where they're written to NVRAM before being written to disk. NVRAM mirroring also takes place over the fiber channel network between both sites. Separate 16 gigabit per second fiber channel virtual interface FCVI connections from the controllers are used, and these get connected into the fiber channel switches again. So I have an FCVI connection from each controller going to both fiber channel switches in the same site. So you see those are the connections for site 1 controller 1. I do the same for site 1 controller 2 and for the 2 controllers in site 2 as well. For the node initiator connections for our reads from disk and for our writes during consistency points, we've got 2 node initiator connections from each node to each switch. For the FCVI connections, which are used for the initial NVRAM mirroring between the 2 sites, we've got a single connection from each controller going to both switches in the same site. The node initiator connections can use a standard fiber channel port on the controller. The FCVI connection has to use a dedicated 16 gig connection. SVM, LIF, volume, and LUN configuration information is replicated between the 2 sites using CRS, the Configuration Replication Service. CRS replicates over a standard IP network using cluster peering and intercluster lifts, the same as we use for our SnapMirror traffic. So we've got three different types of connections on our controllers. We've got the node initiators for connectivity to our disks, that's going over fiber channel. We've got the FCVI for the NVRAM mirroring, which also goes over the same fiber channel network. And we've got the CRS connectivity, which uses intercluster lifts going over an IP network. Cluster identity is preserved during a switchover from one site to another. If a site fails, clients connect to the same IP addresses or WWPNs that they were using before on the original site. The client data network must therefore span both sites. Because clients connect on the same IP address, the same layer 3 subnet has to be available on both sites. You can use dark fiber, an MPLS Layer 2 VPN service, or a proprietary solution such as Cisco Overlay Transport Virtualization for client protocols running over IP, like NAS or iSCSI, or a SAN fabric that spans both sites for fiber channel. So MetroCluster for clustered data ONTAP came out in version 8.3.0. It only supported 4 node clusters in that original implementation. When ONTAP 8.3.1 came out, it also came out with support for 2 node MetroCluster. With 2 node MetroCluster, both sites host an independent single node cluster. And of course, the sites can switch over in case of a failure. There's 3 different supported 2 node configurations. We've got Stretch MetroCluster, Stretch MetroCluster with SAS Bridges, and Fabric MetroCluster. We're going to look at those in turn. So first up, Stretch MetroCluster. In 2 node Stretch MetroCluster, the controllers are cabled directly to the disk shelves with NetApp proprietary long reach SAS cables. Fiber channel switches and 8.0 fiber bridges like we use in Fabric MetroCluster are not used, they're not required. The maximum distance here, because we're using SAS cables, is not going to be as long as fiber channel, it's up to 500 meters. Looking at this, you'll see it's very similar to standard high availability. The controllers are connected to the disk shelves using SAS cables. The difference is that for the NVRAM mirroring, rather than using the standard HA connection, we've got that fiber channel VI connection. It's cabled directly between the controllers, between fiber channel ports. The next type of 2 node MetroCluster that's available is Stretch MetroCluster with SAS Bridges. Here, the controllers are cabled to the disk shelves not directly, but via 8.0 fiber bridges. The controller to fiber bridge connection uses fiber channel. Fiber channel switches are not used here like they are in Fabric MetroCluster. And again, because we don't have those fiber channel switches, the maximum distance is 500 meters. Looking at the diagram, you can see that the controllers have a single fiber channel connection to the 8.0 fiber bridge in both sites, and the 8.0 fiber bridge then has a SAS connection going to the disk shelf, and those SAS connections are daisy chained down through the stack. Again, between the 2 controllers, we've got the FCVI fiber channel connection for the NVRAM mirroring. And the last type of 2 node MetroCluster we have, again it came out in version 8.3.1, is 2 node Fabric MetroCluster. The system is cabled the same way as for 4 node Fabric MetroCluster, which was supported on 8.3.0, so it's very similar. The maximum distance here is increased to 300 kilometers rather than the 200 kilometers. So looking at the diagram, you'll see it's nearly exactly the same as it was for the 4 node Fabric MetroCluster, but we just have 1 node in each site. We also had an improvement when ONTAP 9 came out as well. ONTAP 9 supports 8 node Fabric MetroCluster. With the 8 node configuration, we have 2 HA pairs located in both sites. Each HA pair is replicated to its secondary HA pair at the other site. The maximum distance is 200 kilometers over fiber channel, or we can go up to 300 kilometers if we use the new option of FCIP, which is fiber channel over IP. So those are the supported configurations. Let's look to see what we do if we actually do lose a site now. If a node undergoes a panic in a 2-node MetroCluster, then automatic switchover will occur. For sure, we would want a switchover if that situation happens, so that's why it happens automatically. In other cases, switchover occurs manually or through the use of MetroCluster Tiebreaker software. This is to prevent a split brain scenario where both sites lose connectivity with each other and assume the primary role for all aggregates. We need to avoid a split brain scenario at all costs, because it would lead to different data being written to the plexes for the same aggregate in both sites. Clients in site 1 would be writing to aggregate 1 there. Clients in site 2 would be writing to their plex for aggregate 1 in site 2, and we would have 2 different inconsistent copies of the data in the same aggregate. So we need to make sure that that doesn't happen. The situation that would lead to a split brain would be where both sites are up, but they lose connectivity to each other. And this is why switchover doesn't happen automatically by default, because normally each site wouldn't know if it lost connectivity with the other side, whether that side had actually gone down or if it was just the network that had gone down. So the first way that we can initiate a switchover is by doing it manually. Here, the administrator verifies that a site really has gone down and we do need to switch over to the other side. The command to use is MetroCluster Switchover. If we enter the command while both sites are still available, this will perform a graceful negotiated switchover. So you would do that if you wanted to take a site down for maintenance. The other command we can use is MetroCluster Switchover Forced on Disaster True. We use that to force a switchover when a site has actually failed. Now, the issue that you might have with doing a manual switchover is obviously this is going to take some time. It's going to take some time for the administrator to learn that a site has gone down, to verify that, and then to manually enter this command. So you might want to speed things up, and we can automate it by using MCTB, the MetroCluster Tiebreaker. This is a Red Hat Java application that runs in a third site which has got connectivity to both clusters. It's used to independently monitor both sites, and it will send SNMP alerts if issues are detected. It can also be configured to automatically switch over in the case of a site failure. Recovery time objective, the RTO, is 120 seconds for automatic switchover when we use MCTB. The way it works is it establishes secure shell sessions with each node's node management IP address to verify that they're up. If the SSH session to a node goes down, MCTB will first check the HA status within the site to see if it's just that one node that has gone down and it's failed over to the HA pair in the same site. If it can't reach either node of an HA pair, then they'll both be declared unreachable. But at this point, again, we've only just verified it from one site, so how do we know that it's not just the network from the third site to the HA pair site that's gone down? So we want to verify this again, we double check it. MCTB will then ask the other site via SSH if it has connectivity over the FCIV connection or the intercluster IP network. So in this case, if the third site where MCTB is, it has lost connectivity to, say, site 1. It then asks site 2, hey, have you also lost connectivity to site 1 over both your FCIV fiber channel connection and your IP network? So in that case, there's 3 different networks there that have gone down as far as the connectivity is concerned. We can be pretty sure in that case that the site is actually down. So in that case, you can have MCTB just configured to send you an alert, or you can also configure a rule which will cause an automatic switchover in that case. The last thing to tell you about is MetroCluster interoperability with our other data protection technologies. It can be used in conjunction with SnapMirror and SnapVault. For example, MetroCluster could be used to provide synchronous replication between two sites within 300 kilometers, and SnapMirror could be used to asynchronously replicate the same data to a third site with no distance limitation. So say we've got a site in New York, and we've also got a site in Philadelphia. They're within a couple of 100 kilometers of each other, so we could use MetroCluster to get synchronous replication between those two sites with an RPO of 0. But maybe we're worried that we're going to have a regional disaster, like maybe flooding affects the entire east coast of the US. So in that case, we could also use SnapMirror to replicate the data asynchronously to London. As well as SnapMirror, it can integrate with SnapVault as well, so the data could also be backed up offsite with no distance limitation with a SnapVault backup.